Ever wondered how sound waves behave inside your body during an ultrasound? Let's break down sound attenuation. So, what exactly is attenuation? Simply put, it's how sound loses energy as it travels through your tissues. Imagine yelling across a foggy field. Your voice gets quieter the farther it goes. Inside your body, the same thing happens to ultrasound waves. Some of that energy gets absorbed and turns into heat. It's a tiny amount, but it matters. Absorption is just the beginning. The real star of attenuation is reflection. Picture this. Sound waves hit a boundary between two tissues, like a ball bouncing off a wall. Some energy reflects back, some pushes forward. How much comes back? That depends on the angle. If the sound hits a big, smooth surface, like your diaphragm, at 90 degrees, that's a specular reflector. At normal incidence, almost all the waves bounce straight back to the probe. That's why cysts and organ capsules look bright and clear on scans. If the surface is rough or angled, things get tricky. Enter diffuse reflectors. These scatter sound in every direction. Only a little returns to the probe. Those boundaries look blurry and shadowy on the image, like washing out a chalk drawing with water. For tiny structures, the texture of your liver, the texture of your pancreas, we get scattering. When the tissue's size matches the wavelength, reflections scatter everywhere, creating that soft, grainy look. If the structure is even smaller, like a red blood cell, we see Rayleigh scattering, where sound is scattered equally in every direction. Now, refraction. This happens when a sound wave bends, passing from one tissue to another with different speeds. Like a straw in a glass of water, it looks bent. Two things are needed for refraction. The wave must hit at an angle and the tissues must carry sound at different speeds. No angle or no speed difference, no refraction. There's a rule, Snell's law. It tells how much the wave will bend based on speeds and angles. If aligned just right, you can hit a critical angle where no sound passes. It just skims the surface. Finally, as sound travels deeper, it spreads out, divergence. Imagine a flashlight beam getting dimmer as it widens. That's why deeper structures look fainter on ultrasound. Next time you see an ultrasound image, remember, behind those gray and white patterns is a world of bouncing, bending, fading sound waves, all shaped by the physics of attenuation. Science is pretty cool, right?